Okay, stats, this is section 9.3. Lots easier than section 9.2 because this formula is smaller. But this one is coming from dependent samples. So we talked about last time about independent samples, samples that didn't really have anything to do with each other. You kind of had two data sets, but these ones are going to be dependent samples, okay? So like an example of a dependent sample, let me make this bigger. Example of a dependent sample would be like, let's say I take you 7 students, okay, there's 7 of you guys in this class, and I want to compare the average that you guys have in stats, and I want to compare the average that you have in an English class, okay? So I want to compare your English grade to your stats grade, okay, and see how those averages pan out, the students who have a 95 in my class, do they also have a 95 in English? Students who have an 80 in my class, maybe they're scoring in the 90s in English, that type of thing. So when I compare those averages, those are going to be dependent samples because the students are the same for both of the two categories, okay? So in that case, we have matched pairs because for every stats grade I have, I will have an English grade because there's one student representing each one, okay? So dependent samples, they have some, I'm just going to go through this formula and we'll talk about what some of these variables mean. So you're going to be on the T-chart every single time for this one, okay? Because you're not going to have any data sets that are going to be larger than 30. So you're going to be using this table every single time. All right. Then they have some weird things going on. They have D bar is what they call it. And D bar is going to be the average of the differences. Okay, so what they will do is they will have a data set here and they will give you these two rows of information here, okay? And so things that we have that we're comparing actresses and actors. And they have matched those up so that we have the same number of actresses, the same number of actors. And then what they do is they compute the differences, and that difference just means subtract, right? So I take 28 and I'm subtracting 62 and they got negative 34. 28 minus 37, they got negative 9. Okay, so you're just subtracting the two values from each other. You usually take the first one, so when you're doing the difference, you take the first one minus the second one, okay? And that's how you get your differences there, okay? So the difference is just going to be the average, or D bar is going to be the average of those differences. So we'll do that here in just a second. I'm going to find the average, the mean of those values, okay? That's what D bar is. Your mu D is always going to be 0. That's what our hypothesis is going to say. And then standard deviation of the differences, that's what SD is. So SD equals standard deviation of the differences. So I would take this column right here, or this row right here that I get from the difference values. I would find the average, that's going to be D bar. I would find the standard deviation, that's going to be SD. And then I have the square root of n, which in this case is just going to be 5 numbers, okay? So even though there's 10 numbers altogether, n is still only going to be 5 here because I have 5 pairs, basically, okay? So this is what we have going on here. They say actresses, are actresses generally younger than actors, okay? So, I think we've talked before about they always pick on the actresses versus the actors because evidently men age better than women. I don't know why that's a thing. It's totally unfair, but whatever. So actors a lot of times can be older than actresses because men don't age. Somebody that's in their 40s can still look like they're 30 years old. But actresses, not a whole lot of actresses exist past 45 years old. They want them all younger than that. So what we're doing is we're looking at the average age for each one of these and saying, okay, is the average for actresses younger than the average for actors? And we're comparing the two, saying, is that a thing? Do they pick the actresses to be younger? So that's what we're testing here. Here we're considering one aspect of how we treat women and men differently based on their ages. When we get down, the ages are matched according to the year that the awards were presented. Okay, that's why they're coming in pairs. So they're doing Best Actress, Best Actor award for, I don't know, probably the Academy Awards or something like that. The ages are matched. Let's see. Use the sample data with a 0.5 significance level. I'm going to put that over here somewhere. 0.05 significance level. To test the claim that the population of ages of best actress and best actors, the differences have a mean less than 0. Okay? So when they have a mean that's less than 0, what that means is you're saying that mu1 is equal to mu2, just like we had before. So my hypothesis is still going to be that mu1 is equal to mu2, except when they talk about 0, they're saying, a lot of times we'll write mu1 equals mu2 as mu1 minus mu2 equals 0, okay? Because they'll subtract that mu2 over to the other side. So this is another way of writing this, and that's what they're saying here. So they have a mean less than 0. If they say that, they're just wanting to test to see if they're equal or not, okay? So that null hypothesis is going to go with my claim. This one is going to be that the averages are not equal, okay? So the average age is not equal. Now, which one is mu1 and which one is mu2? In the table, according to this stuff, they have actress listed as the top one and actor listed as the bottom one. So we'll do mu1 is going to be females and mu2 is going to be males, okay? Just because that's the way that it's in the table, okay? Actress, actors 1 and 2, okay? All right, so for test statistic, we need some of this information. I need to know what d bar is. I know what mu d is in the formula. Mu d is always 0, okay, because that's what this guy right here is. Mu1 minus mu2, another term for that is mu d, the differences of the two, because we're subtracting those two. So the differences of my averages are going to be mu d. I need to know what SD is, and I need to know what N is. So I really only need those 3 pieces, and then I can do my formula and be done, okay? So the way easier than the first part, or section 9.2, when you don't have matched pairs. I like this section a lot better. We already said our N was 5 because we have 5 pairs, okay? Then I just need to find the average of these guys and the standard deviation. So what I went ahead and did is I put this on a spreadsheet here, okay? And suppose you don't want to have to subtract each one of those every time, okay? I went ahead and set up my table. I have my actresses, my actors. What I can do is enter a formula in here, and you can do this on Google Sheets too. So equals, I would say this guy minus this guy, the first one minus the second one, and it gives me negative 34, just like it has in the table over here, okay? And then what I can do is, rather than typing that in 4 more times, I can take this like little bottom crosshair, okay? He turns black, and I can drag him over and he will give me those numbers, okay? So negative 9, negative 5, negative 9, and positive 6, okay? Now the 2 things that I need from here are to know what the averages and the standard deviation is of those 5 bottom numbers, okay? So I'm going to do average here, and I'm going to do standard deviation, okay? So equals the average, A-V-E-R, average. It's going to open up my data set, and I'm going to say these 5 numbers, okay? And I'm going to hit enter, and my average is going to be negative 10.2. Okay, my standard deviation then equals STDEV of those 5 numbers. Okay, enter. And 14.65 is going to be my standard deviation. So let's write those numbers down. Negative 10.2 standard deviation, 14.65. We'll just do 2 decimals this time. Okay, so for my formula, I'm using this guy up here. D bar is going to be negative 10.2 minus 0. So you really don't need to have that 0 there. And then I have the standard deviation, 14.65, divided by the square root of 5. That's what he will look like. Okay, so if I just put this all into my calculator at one shot, I will have negative 10.2 divided by, I'm going to open up a parentheses, 14.65 divided by the square root of 5. I'm going to close that parenthesis, and then I'm going to close my parenthesis that was in front of the 14.65. And that guy is negative 1.56, just about. Okay, so that's what he is. That's his, your test statistic, your T. Okay, all right, now, since I was saying equal, I'm going to have a 2-tailed test. One here, and 5% split up into both of those is 2.5%, and 2.5%, which means 95 in the middle. Okay, When you're doing mean, so when you're doing section 9.2 and 9.3, these are all means. Okay, we did proportions in section 9.1, section 9.2, 9.3 is mean. Standard deviation and variance is what we're going to do in section 9.4. I said p-value is not as easy to do with means just because of the way that the table is set up. So we're going to go ahead and do the critical value method every time we do a mean. And so what I'm wanting to look for is where these two cutoff mark numbers are with a 95%. Okay, so I get my t-chart out because this is the one you're using every time. 95% is going to be this column right here, and then I need to figure out how many degrees of freedom I have. Okay, so degrees of freedom is still going to be n minus 1 over there, okay? And my n was 5, so I really only have 4 degrees of freedom here. Okay, so I'm all the way up at the top of this chart, and I am in, what was that? Yeah, it should be 2.776 is what my t is going to be. So this one's negative 2.776 and positive 2.776. Okay, and then I figure out where my number here lives in between those. Like this has 0 in the middle. Negative 1.56 is going to be right here somewhere. Okay, so we're still in the clear, which means that according to the critical value method, we're going to fail to reject the null hypothesis. So basically we're saying that the averages are equal to each other. Okay, the claim is valid. Claim is valid. We're saying that those two averages are going to be equal to each other. So just as one more conclusion, we'll say that actors are same age as actresses. Okay, and that's the conclusion just based upon this data. Now again, we're only given 5 data points, so maybe given a different data set, we would have a different conclusion. That's why we never say accept the null hypothesis. We just fail to reject it given this information. Okay, because if we're given another data set that maybe had 20 years worth of data in it, maybe it would lead us to actually reject the null hypothesis because the ages were different. So we only say fail to reject. So according to this, the actors and actresses have the same age. Okay. I'm going to go ahead and wait until the next video to do section 9.3 or the confidence interval method, just so these videos aren't too long. But what I'm going to have you do is do number 1. You're just finding the value of d bar in the standard deviation, so you will need to use your your Google Sheets, probably table, and you'll have 5 data points there. And then let's go ahead and let's just have you do the odds again. So 1, 3, and 5. Okay, 1, 3, 5. Yeah, we'll do that. Okay. All right. So you can start working on part A. 1 you can do all the way through. 3 you can do part A. 5 you can do. There's really not a part B, but I'm going to add a part B. So part B is the confidence interval, but you will do this after the next video. Okay. So there's that. All right.